Hello, my name is Chang Lee, President of AQS and Journal Club Manager of QISCA. It is my pleasure to introduce today's Journal Club speaker, Yoonjin Bae from SQRT. Yoonjin is the senior at the Department of Physics and Astronomy at SNU and President of SQRT, SNU Quantum Research Team, since August 2024. From December 2023 to May 2024, she was undergraduate intern in Laboratory for Integrated Quantum Systems, which led by Professor Do-Hoon Kim, and currently undergraduate intern in Quantum Device Lab led by Professor Eun-Jong Kim since August 2024. Her main research interest is superconducting qubit implementation and quantum error correction. Today she will be presenting a talk titled Continuous Time Paths Recovery Map, Concept, Dynamics, and Potential Implementations, sharing insights from the paper Reversing Link Path Dynamics via Continuous Paths Recovery Map by Hyuk-Jun Kwon et al. Please join me in welcoming Yoonjin to the stage.
Okay, thank you. I am Yoonjin Bae, and I am an undergraduate intern in Quantum Device Lab at SNU with advisor Professor Eun-Jong Kim. And today I am going to have a presentation with the title Continuous Time Path Recovery Map, Concept, Dynamics, and Potential Implementations. So today's presentation is based on the paper titled Reversing Limb Dynamics via Continuous Path Recovery Map, written by Professor Hyuk-Jun Kwon and two other authors. So let's get started. So today's outline is shown below. First, we will begin with the brief introduction to path recovery map and look what is path recovery map. And next, we will look into the applications of this framework, especially for some QEC codes. Then we will take a closer look to practical implementation, especially for the superconducting circuit QED, and share some of the work that my advisor and I have been doing on how to implement this path recovery map. So, let me briefly review some basics to the Lindblad master equation first. So the Lindblad master equation is the equation describes the evolution of the density operator of an open quantum system. And as you can see, the time derivative of the density operator is expressed like this. So this equation consists of two main parts. The first one, the colored in blue, shows the linear evolution with the system Hamiltonian H. And the second one, the color in red, is the shows non-unitary evolution governed by some dissipators and the jump operators denoted as L mu. So each jump operator induces some kind of decoherence and dissipation. So overall, the system, starting from the t equals 0 as a state gamma 0, evolves into the t equals tau as a gamma tau. So we have reviewed what the Lindblad master equation is, and some natural question will arise that if the state at the time tau is given, then is it possible to recover the original state from the gamma tau to the gamma 0? So in other words, can we reverse the effect of this second non-unitary evolution? So this is some kind of important and central question in quantum information. And in this presentation, we'll look at how the path recovery map provides a way to solve it. To address this question, let's introduce the path recovery method. So for reference state row and the CPTP map N, the path recovery map is defined as the following composition of mass as below. And as you could expect, the N will be quite noisy channel, including the parts that we don't want. Essentially, this map attempts to recover the original state row from the noisy state and row. So we can easily prove it. As shown below, if we put the expression below, then we can you will go back to the initial state row and assuming the ideal condition is met. And this diagram illustrates the ideal clearly, and we go forward to the end row with the noisy channel. And applying the path recovery map denoted as R, we can go back to the initial state row. So for the intuitions, let's think of some analog of this path recovery map in classical channel. So let's think of some distribution Px, and let's think that it will evolve into the Py. The relation between the Py and the Px will relate it with this Py to y of x, representing the conditional probability. So from the base rule, we can reversely find the Px from the Py with this expression. So more precisely, if we know the Px of y and Py of x, and the Py, then we can compute the Px in reverse. So analogy to this, we will think as a distribution Px as a initial state row. So if we do this, then we can see this inner term as a Py, and this multiplying the n row at the front and the back can be think as a kind of normalizing the distribution into some kind of Py. Secondly, this second inner term can be think as a Py of x, because it is covered with n, showing the same part here, and same part here, and here. And finally, multiplying by row at the front and the back can be interpreted as a Px. So similar to the classical probability distribution, the path map can be thought as a reconstructing the row from the end row, the noisy state row, using the structural information about the channel. So in this way, the path map can be seen as a quantum analog of Bayes' theorem. Again, suppose we start from some reference state denoted as gamma 0, and it evolves to the gamma tau under some kind of noisy CPTP map N. Then the path recovery map denoted as R can perfectly recover the gamma tau into the gamma 0. But what if we want to recover the state, not just the initial state, but the intermediate state, or start, if we want to start at the intermediate time, then we can think of like this. So as the Lindblad equation satisfies the semi-group property like this, and thanks to this structure, we can construct the recover map for the extended arbitrary time for the t from the 0 to tau. So in other words, instead of single backward from the t equals tau to t equals 0, we can now have a continuous time recovery protocol that covers from t equals tau to arbitrary time t. So now we have extended the path recovery map to the continuous time, so we can think of continuous path recovery map. So now we can ask, how is the recovery map described in the infinitesimals level? And in the limited infinitesimal time, the path recovery map can be described as a Lindblad equation like this. So it is also similar with the equation I showed earlier, and is combined with the two major terms. The first is the backward Hamiltonian, and the second one shows the dissipator generated from the backward jump operator. So, and you can and the tilde t's indicates the backward direction, and which can be also think as kind of tau minus t, and uh, and I want to mention that both the Hamiltonian and jump operators are time dependent, and they are defined in terms of the original four dynamics. So, um, uh, if we want to express more details of the elements in this expression, we can solve like this. And I will not go too much detail into this or some kind of proof, but the key point we have to know today is just one thing. Although this expression is quite complex, it is eventually represented with gamma t for some time t. So this tells that the recovery dynamics is itself governed by the proper Lindblad equation, just like the four dynamics. And the figure and this right figure shows the key point of the path recovery map. So for dynamics is shown in the blue line, and it is described by the Hamiltonian H and the jump operators L mu. And also the reverse dynamics expressed with this left Lindblad master equation is shown in the red line, and starting from the tau to the time 0, it can be described by Hamiltonian HB and the jump operators LB mu. And the reverse jump operator, as you can see here, the reverse jump operators can be implemented by interaction Hamiltonian between the original system and other environmental ancilla. And this ancilla should be strongly decaying, and I will mention this later. Now let's consider the scenario where the forward and recovery dynamics simultaneously act in the system like this. So in this situation, the Lindbladian can be described like this. So the LF plus LB, which the LF shows the forward dynamics and the LB shows the backward dynamics. And the effect of this in Lindbladian is quite trivial, that for the state called the reference state or gamma, the time derivative of the gamma should be 0. And we can interpret this as instead of reversing quantum trajectory, we are in effect of trapping a fixed reference quantum state gamma. So we are not we are not changing or evolving the quantum state gamma from the gamma 0 to gamma tau, but trapping or fixing the reference state at just one gamma. And this comes from the infinitesimal time recovery LB. The backward dynamics cancels out the noise F. So let's move on to the application to the continuous path recovery map. So we have shown the some basics to the basis of the path recovery map, and one of the important features of the path map is universal recovery property. So this path recovery map can recover not only the reference state, but it is known that it can also recover the higher ordered Hilbert state, Hilbert space. So for example, let's consider a fully connected n-spin change denoted expressed as like this. So then we can let the logical qubit as spanned by the degenerate ground states shown in like this psi. And if we set the reference state as gamma in the expression of like this, then after this, we can consider the bit flip noise after this encoding. So the result is shown right. So there is, so in the plot on the right, you can see the px. The px is the probability of the bit flip noise, and we will investigate how the recovery works. And as the px, I mean the bit flip probability increases, we can easily intuitively know that the 1 minus FAV, I mean the fidelity, average fidelity will increase because as the bit flip error increase, fidelity will decrease, and the 1 minus FAV will increase. So this means the best situation. But if the beta decreases, as the px increases, we can see in this figure that the beta threshold decreases like this. And this means that the beta threshold decreases from in this figure to the left side. Then we can know that the required recovery strength decreases because as the beta beta decreases, also the recovery strength decreases. And we know that this is a good situation. So we can think that this is kind of a trade-off. So even the px increases, it is not always bad, but the recovery strength could be the required recovery strength can be decreased. So the conclusion is that the weak recovery dynamics can be effective for some intermediate noise level, considering this two trade-off. Now we know that we can recover the larger Hilbert space. So let's put into the quantum error correction code. So assume that the code space C is spanned by quantum states commuting with stabilizer S. So, and for the subset of the stabilizer bar S in S, the recovery dynamics becomes like this. And just like earlier, I will not get much detail or proof of this today. But we know that this structure is just like the form of the continuous syndrome QEC. And because it is a kind of the linear combination of the stabilizer. And this kind of continuous syndrome QEC is already studied in other papers, so we can simulate with and find some difference with just the classical QEC and the QEC that uses this recovery map. So on the right, we compare several protocols. The green line shows the 5-qubit just standard QEC. And as in the figure, we can see that the sys not differs to the no recovery in 1 qubit. And this means it is not much efficient. But if we just use even the 5-qubit recovery map, we can see the fidelity increases. So 1 minus fidelity decreases. And moreover, if we use the QEC and the 5-qubit recovery map, this decreases very much. So the combination of QEC and continuous path recovery dramatically improves the fidelity, especially in this early time version. So let's compare the resource requirements of standard the classical quantum error correction with those of the path recovery approach. So to implement the reverse dynamics, we will need the n plus n qubits, where the n is the number of physical qubits, and NA shows the ancillary qubits to implement the reverse jump operators, as I mentioned earlier. And also, I will show it later of this page. And for local noise model, it is known that NA increases linearly to N. So it is similar with the number of ancillary qubits required for syndrome measurements in standard QEC. And furthermore, if noise at each physical qubit has pairwise correlation with at most L qubits, it is known that the NA is always bounded with the resource of O n times L. So in terms of qubit overhead, the path recovery scheme is no more expensive than standard QEC. And in some cases, it might even be more resource efficient, especially since it doesn't require real-time classical feedback or control. So you can see here on the left, standard QEC has two sequences. The first one is the syndrome measurement. And after the measurement, we have to do some additional classical computation and conditional control. And we will control the system again. But in contrast, the path recovery map shown in the right shows just one sequence, the just one single time-independent protocol. So meaning that it runs passively without any measurement or feedback during the process. And this can act as another advantage than the standard QEC. But one might wonder, is this method always better than standard QEC? So there's a trade-off. So in fact, it is briefly mentioned earlier, the path recovery map requires the knowledge of the forward state at each time step. So it means we need to compute or track the entire forward dynamics of the system at the previous state. In other words, additional forward dynamics calculation is needed before this time-independent protocol. So while the path map reduces the need for the active control, it comes at the cost of requiring full knowledge of the systems for evolution. Now let's look at how the continuous path recovery map can actually be implemented, especially in circuit QED systems. Let's consider the dynamics of a combined system with qubits and ancillas as we see earlier, and which is governed by the Lindblad master equation. So in this case, the Lindblad master equation can be written like this: the system and which the SA denotes the system and ancilla, and the Hamiltonian can be written like this: the HB denotes the backward Hamiltonian, and the H int denotes the interaction Hamiltonian, and the large gamma 8 shows the dissipation rate. And with this, after tracing out the ancilla, this leads to the effective system dynamics LB, that we need for the path recovery map. But note that this qubit ancilla system and Lindbladian is only approximate value for the range, expressing like this. So where the dissipation rate of the ancilla gamma A is much more stronger than the ancilla coupling strengths, and this coupling strength must be also larger than the dissipation strength of the qubit dissipation strength, denoted as a gamma mu. So, but it is, even with this condition, this condition is possible in circuit QED. So, for example, we can set the gamma A as a 10 megahertz, HSA as a 1 megahertz, and gamma mu as a 100 kilohertz, and we can see that this condition is satisfied here. So in the time-independent recovery protocol, we assume that both the Hamiltonian and the jump operators are linear combinations of Pauli operators like this, because we already saw the ancilla as a two-qubit system. So each of the HB and the LB can be written like this. And realizing such jump operators requires the protocol calls dissipation engineering, which engineers this interaction Hamiltonian. So let's introduce a strongly decaying ancilla that interacts with the qubit via like this. So this corresponds to the part here. So now we have to engineer the interaction Hamiltonian H int and make a path recovery map that we want to make. And in those limit the strong ancilla dissipation, we can automatically eliminate excited states of the ancilla, so we can satisfy these two conditions. So in the So in the paper, it shows one simulation that shows the simulation of the qubit and ancilla system, and this is the result of that. So when it starts from the 0 state, and because of the dissipating rate is and the t covariance it goes through this. But because of the ancilla and qubit system, Hamiltonian and this interaction Hamiltonian, this can be go reversely like this. And also I have my advisor simulated this, and as I said earlier, the ancilla dissipation rate should be very much stronger, and we have seen whether it is right. So as we can see here, as the ancilla dissipation rate increases from the 1 to 10, 50, we can see that the system follows the trajectory more accurately, and in the dissipation rate 50, it shows this very similar work as a paper. So let's move on how the continuous path recovery might actually be implemented in a circuit QED system. And from this point then, the content is not from the paper, but rather based on the work my advisor did. And of course, it's difficult to address every general case, so let us narrow the focus. So here's the question. Implementing the path recovery requires time-dependent control over jump operators, and how can we make things simpler? And especially for the transform qubit, it is known that the dominating source of dissipation is that due to dephasing besides energy realization. And this corresponds to the single jump operator L expressing like this. And this yields the following explicit expression for the Hamiltonian and jump operator required for addressing the qubit. And after calculating, we can find that the interaction Hamiltonian is expressed like this. And here are the references I used in this talk, and that concludes my presentation. And if you have any questions, or if you like to share thoughts or suggestions related to this work, please feel free to reach out via this email or LinkedIn. And thank you for your attention.
Thank you for the excellent talk, and feel free to ask to the presenter.
네.
I have a quick question.
아.
Sorry.
이쪽에서 먼저 질문이 있어서.
Okay.
네. 아날로그 방식. 네, 그렇습니다. 결국에는 네, 그러니까 So the question was if whether we need to use a different techniques to make this interaction Hamiltonian for each platforms, and it is right. And I have suggested the Sear gate and parametric modulation for implementing this interaction Hamiltonian, but for other platforms like ion trap or neutron atoms, it should use another techniques. And as long as I know, the trapped ion is much simpler to implement this Hamiltonian. 아마 관련해서 이제 그거를 구현한 아카이브가 5월달인가 6월달에 나온 것이 있는 거예요.
So I have a quick question.
네?
So what's the, I guess, selling point of the continuous Petz recovery map? When would I want to use standard error correction, and when would I want to use the Petz recovery map?
There's a trade-off. So, for the QEC, the standard QEC, it uses digital computation and control, but the path recovery map depends on the just only analog modulation and techniques. So, if the platform is suitable to the analog techniques, then I think it will much more great to use the path recovery map.
Can you give an example?
네.
Can you give me an example?
어, 글쎄요. 음,
Okay.
네, 좀 더 자세한 것은 잘은 모르겠습니다. 근데, 일단 패치 리커버리 맵을 쓴다는 것 자체가, 그러니까 버젯에 대한 거는 제가 리소스나 버젯에 대한 거는 더 자세하게 찾아보지 않아서 정확히는 모르겠지만, 일단 이 논문에서 나왔던 버젯만 따지자면, 그냥 QAC를 하는 것보다 리커버리만 했을 때, 세상에 이제 dissipation rate이 0. 거의 0.01 이상부터는 얘가 더 높은 피델리티를 보이는 것을 모아서 그게 더 통상적으로 낫지 않을까라는 생각은 듭니다.
So what do you mean by a time independent protocol? What does that mean exactly?
아, 뭐지? 네, 그냥 한글로 잠시 설명을 드리자면, 타임 디펜던트 프로토콜의 경우에는 일단 t가 제로일 때 이제 타워까지 그냥 갔다가 다시 돌아오는 걸 얘기를 하는 거고, 타임 인디펜던트는 그냥 얘를 이제 backward랑 forward랑 같이 하면서 동시에 네, 정재훈 씨께서 말씀하셨던 것처럼 실시간으로 하는 거를 생각하시면 됩니다.
So why is it time independent? Isn't it real time protocol then?
네?
So you said that it's performed in real time, I guess, but then if it's why is it called the time independent protocol if it's just
이제
performed in
예를
real
들어서
time?
제가 이제 요 시뮬레이션 같은 경우에는 여기 제로 스테이트에서 이제 디코헤런스가 되면서 내려감다가 다시 얘를 돌리려고 한다면 시간마다 이 인터랙션 해밀토니안을 다르게 줘야 될 텐데 이제 계속 이 제로 스테이트에 고정을 시킨다고 하면 그거는 타임 인디펜던트하게 계속 똑같은 것만 주거나 아니면 주기 때문에 그걸 타임 인디펜던트라고 부르는 거고요. 그리고 여기에서 가정하는 점이 아까 언급은 안 했지만 어딨냐? 해밀토니안이 타임 인디펜던트하다는 가정을 갖고 있습니다.
Oh, so you perform the same operation regardless of the state.
님 스테이트가 고정이 되기 때문에 그거를 계속 하나로 줄 수가 있는 것이고 그 이니셜 스테이트가 어디냐에 따라서는
So it only depends on the initial state.
예,
Not the
예,
state
예, 예, 그렇습니다.
after t equals 0. Okay, okay.
I also have a question.
아, 잠시만요. 이쪽에서 질문이 있어서. 그거는 잘 모르겠습니다. 근데 여기에서 쓰는 엔실라가 같이 안 될 잘 모르겠네요. 근데 안 될 것 같긴 한데 이따가 같이 생각해 볼게요. The question was whether we can use the same ancilla for the QEC and the past recovery map, but I'm not sure whether we can use the same ancilla, but I think we cannot because after we used the past recovery map ancilla and it is expressed here, and this protocol is wait, I'm not sure about this. Sorry. I heard that there is another question from Songbin Lee.
Yes, that's correct. It's a simple question. So the Petz recovery map assumes that the qubit follows the Lindblad-Master equation. Is that correct?
Yeah.
And Lindblad-Master equation is valid when the system follows the Markovian process. Basically means that it is path independent. How valid is that assumption? Like I believe traditional quantum error correction codes like surface codes, color codes, 5-qubit codes, or CSS codes does not need certain assumptions, right?
Yes.
How much the transmitted qubit is Markovian? Like how much it is path independent? Like do you have any kind of qualitative figures on how qualitative figure measures on how it is like Markovian?
Sorry, but I think I cannot answer to that now. 네. 네, 그게 이제 정량적으로 얼마나 되는지가.
Yeah,
네.
but like just a quick comment on that. Doesn't like a certain QEC require the errors to satisfy a certain condition in order to be correctable? Like I don't think you can use QEC to correct a non-Markovian error, right? So I guess that evens things out.
Like
그런가요?
QEC corrects Pauli errors.
Yeah, but I don't think you can use it like I don't think you can use the surface code to correct a non-Markovian error. I think that's like an active area of research. So or maybe I'm wrong, but yeah.
Every unitary error can be represented as a linear sum of Pauli errors. I'm not sure it's that same as Markovian errors, but like anyway, so I guess the term of how non-Markovian process can be corrected, I guess that's still an active research field.
I know, yeah, probably like yeah.
Okay, thank you.
If there's no more question, thanks Yunjin again for the excellent talk. Thank you for attending to today's introductory seminar and journal club.